Namaste. The second presenter, Dr. Deepa Khare from the Department of Biotechnology, Bennett University, Greater Noida, India, delivered a comprehensive presentation on CRISPR-Cas9 mediated metabolic engineering of white rot fungi for the production of industrially valuable products from agricultural waste derived lignin. The presentation highlighted the major source of agricultural waste generation in India and emphasized the importance of recycling agro waste for industrial applications, thereby addressing issues such as stubble burning. It further explained the conversion of agro waste derived lignin into vanillin through the application of CRISPR-Cas9 technology integrated with AI-based algorithm in white rot fungi. The presentation clearly demonstrated how artificial intelligence simplifies and accelerates the metabolic engineering processes, streamlines complex biological pathways, supports environmental sustainability, and enables the efficient production of industrially important value-added products. Based on the two presentation, in my view, the second presenter's talk more clearly demonstrated how artificial intelligence simplifies and accelerates the metabolic engineering process, streamlines complex biological pathways, supports environmental sustainability, and enables the efficient production of industrially important value products such as vanillin from the agro waste derived lignin. Once again, I sincerely thank Dr. Arjun Dev, President of Vedant Foundation and CEO of the Vedant Educational Service, for providing me a wonderful and valuable opportunity. Thank you.
Good morning, respected faculty and colleagues. This is Dr. Sana Qausain. I'm Assistant Professor in Datta Meghe Institute of Higher Education and Research in Wardha. So today I'm going to present my topic, my review article, Revolutionizing Protein Science, Advances in Artificial Intelligence for Protein Structure Prediction and Functional Annotation. So I'm the primary author and corresponding author of this paper. My co-authors are Dr. Mohammad Bashiruddin, Mohammad Affan Kareem, Dr. Mohammad Khurshid Alam Khan, Dr. Faiz Iqbal Khan, Dr. Archana Dhok ma'am, and Dr. Ashish Anjankar sir. So let's move on to the next slide. So in this presentation, I will first introduce the topic, then briefly discuss traditional protein structure determination methods. After that, I will focus on milestones in AI-based structure prediction, including AlphaFold and related models. I will then cover functional annotation, drug discovery applications, challenges, future directions, and finally conclude the presentation. So let's move on to the introduction slide. So basically, artificial intelligence has significantly transformed protein structure prediction. Traditionally, understanding protein structure required complex and time-consuming experimental methods and techniques. This review focuses on how AI-based models have emerged as powerful tools to overcome these limitations. We discuss traditional methods, key AI models, their application, challenges, and future perspectives in protein science. So let's move on to the importance of protein structure and biological function. Protein structure is directly linked to protein function. The three-dimensional structure determines how a protein interacts with ligands, other proteins, and nucleic acids. It also governs catalytic activity and signaling pathways. Even small structural changes can disrupt function and may lead to diseases such as cancer, neurodegenerative disorders, and metabolic abnormalities. So let's move on to the traditional method slide. So traditionally, protein structure have been determined using X-ray crystallography, NMR spectroscopy, and crayon electron microscopy. So X-ray crystallography provides high-resolution structures but requires protein crystallization. NMR spectroscopy allows structural determination in solution but is limited to smaller proteins. Cryo-EM is highly useful for large complexes but requires expensive instrumentation. Overall, these methods are accurate but time-consuming, costly, and technically challenging. So this is the table, traditional versus AI-based methods. This table compares traditional experimental methods with AI-based approaches. Traditional methods provide highly accurate and experimentally validated structures, but are slow and expensive. In contrast, AI-based methods are fast, scalable, and rely on large data sets to predict structures directly from protein sequences. AI approaches allow proteome wide structure prediction, making them highly suitable for large scale studies. So let's move on to the next slide. AI based protein structure prediction models. So major breakthroughs in protein structure prediction have been achieved using deep learning methods. Like AlphaFold has demonstrated near experimental accuracy in many cases. Rose TTA Fold uses a multi-track learning approach that integrates sequence, distance, and coordinate information. ESM Fold is based on protein language models and enables rapid template-free structure prediction. So next slide is functional annotation using AI. So beyond structure prediction, AI plays a critical role in functional annotation. AI-based tools can identify active sites, binding pockets, and functionally important residues. This is particularly valuable for newly identified proteins whose functions are unknown, helping to bridge the gap between sequence structure and biological function. So let's move on to the next slide, that is AI in drug discovery. So AI has greatly accelerated drug discovery processes. AI used in virtual screening, molecular docking, and lead optimization. These approaches reduce experimental costs and time by prioritizing promising drug candidates and improving binding affinity predictions, ultimately speeding up the development of new therapeutics. So, what are the challenges and limitations? Despite its success, AI in protein science has several limitations. These include data bias due to incomplete or unbalanced data sets, limited representation of protein dynamics, since many models predict static structures, and challenges in interpretability, where AI models act as black boxes without clear biological explanations. So let's move on to the next slide, future directions. Future developments in this field include the integration of multi-omics data such as genomics and proteomics to improve functional predictions. Advances in dynamic modeling aim to capture protein flexibility and conformational changes. Additionally, AI is expected to play a major role in personalized medicine by enabling patient-specific protein and drug response predictions. Let's move on to the conclusion. In conclusion, artificial intelligence has reshaped protein science by enabling rapid and accurate structure prediction, functional annotation, and drug discovery. While challenges remain, AI complements experimental approaches and holds great promise for advancing biomedical research and therapeutic development. So these are the differences. Thank you so much for listening me and giving me this opportunity. Thank you so much.
Namaste. Vedanta Education Services made commendable efforts to organize the 4th International Virtual Multidisciplinary Conference titled From Gurukul to Global, Paving the Path to Viksit Bharat 2047, Reconstructing Higher Education with Indic Priorities. I had the privilege of chairing a session at this conference. The first presenter was Dr. Sana Qausain, who served as the first and corresponding author for the presentation from the Department of Biochemistry, Jawaharlal Nehru Medical College, Wardha, India. The co-authors included Dr. Mohammad Bashiruddin, Dr. Mohammad Afan Karim, Dr. Khurshid Alam Khan, Dr. Fayaz Iqbal Khan, Dr. Archana Dok, and Dr. Ashish Anjankar. Dr. Sana Qausain presented a topic titled Revolutionizing Protein Science, Advances in Artificial Intelligence for Protein Structure and Functional Annotation. The presentation provided a comprehensive and informative overview of the role of artificial intelligence in modern protein science. The presenter began by elaborating on traditional methods of protein structure prediction, clearly explaining commonly used experimental techniques and highlighting their challenges and limitations. This background effectively set the stage for introducing AI based approaches. Dr. Sana Qausain then explained AI-based protein structure prediction methods and functional annotations, emphasizing how machine learning and deep learning models have significantly improved prediction accuracy and speed. She clearly describes the crucial role of AI in bridging the gap between DNA sequence information and protein structure and function, helping the audience understand how AI decipher complex biological relationships that were previously difficult to resolve. The presentation was well organized and delivered in clear and understandable manner, making the concept accessible to broad audience. The use of recent references from 2021 to 24 strengthened the scientific relevance and demonstrated an up-to-date understanding of the field. As the work was presented in the form of review article, it provided a general and holistic overview of AI applications in protein prediction. However, the evaluation notes that the presentation could be further enhanced by including specific examples or case studies to illustrate AI-based structure prediction and functional annotation methods in practical scenario. This would add depth and improve conceptual clarity, especially for learners new to the field. Overall, the presentation was informative, scientifically sound, and clearly communicated effectively, helping the audience understand the fundamental concept of AI-driven protein science. With the illustration of with the inclusion of illustrative examples, the work could be further strengthened and made even more impactful.